Yeah, he arrived. He didn't say yet whether he wants to do it in Etherpad or not.
So do we have a second?
I don't know. Stephen, can you give me a hands up, hands down whether you're doing Etherpad? Yes, no? Okay, so Stephen will minute in the Etherpad. If people want to help him minute, that would be excellent. Also, if you speak at the microphone here, you might want to pop into the Etherpad to see that what was captured is correct. Specifically, also maybe your name is correct at least. You can get to the Etherpad from the agenda page. There's a whole row of buttons. One of them gets you there. Right, and I think we're moving ahead when Phil is ready with the slides. Are you downloading them all? Okay. For the remote people, the Meet Echo guys informed me that for some reason the Meet Echo Jabber isn't connected to the IETF Jabber room, which we're going to be using for the BOF. So if you're remotely and you want to comment, please join the L4S@jabber.ietf.org room. If you type things into Meet Echo, we're not really going to see it, I think. I'll try and keep an eye on that room, but if I'm missing something because I'm up here, anybody else is welcome to relay from the floor as well. This time we're handing out the blue sheets immediately at the beginning. Anyway, so I'm Lars Eggert. This is Phil Erdley. We are the BOF chairs for this. We're not the BOF proponents. Want to make this clear. We are here to run the agenda, make sure that we're staying on time and we have time for discussion at the end to determine what should be done in this space. Mirja is the AD. I think I've seen her around already. She's right there. Okay.
So welcome everybody. I'm Philip Erdley. So L4S, which stands for low latency, low loss, scalable throughput. We have note takers, we have Jabber. Please remember to say your name at the mic. We have the usual note well. So what is L4S? Are you in the right place? Low latency, low loss, scalable throughput. So I think that just to very briefly say a little bit more about what the BOF is about. So I think it starts from the proposition that latency, and in particular queuing delay, is the factor that limits many applications' performance today and in the future in the internet. So how can we go about overcoming that? So L4S is a set of technologies to try and address this, and it has three basic components that you're going to hear more about. So it's got an updated transport protocol in the end hosts, a new queuing algorithm, or AQM, as it's often abbreviated to, in bottleneck links, and then it needs a new way of identifying L4S traffic against sort of existing or classic traffic, and that's for coexistence or incremental deployment. So those are the kind of three components of the technology that you'll hear about more shortly. So in terms of what's happened so far, so the proponents have done a lot of work already on drafts and on real implementations and experiments. And I think one thing to note is that that way of identifying L4S traffic versus existing traffic is something where we do need new IETF standards work. So that's one of the motivations for the BOF. So the purpose of the BOF, why are we here today? The first reason is to inform the wider IETF community about L4S. There's been some talks about various aspects of it in things like ICCRG in the past, but we wanted to inform the wider community about it. And and then it's to seek feedback about, and I put 4 things there, and those are 4 questions that we will ask people at the end of the BOF. So those are the 4 things to be thinking about during the various presentations. We wanted to put up one thing that we don't really want to discuss today, and we don't really want to talk about sort of organisational aspects of how any work might be arranged amongst IETF working groups. That didn't seem to us like it was likely to be a very productive use of people's time here today. But assuming the work goes ahead, if it does, which we'll get hums on at the end, then Mia, our AD, will be thinking about how to arrange the work, so your views would be very welcome, and talk to her. So here's our agenda that we've got. After this introduction, we've got Bob Briscoe talking about the problem and the kind of very high level solution. We've got Koen, who's going to do a demo of L4S in action. So I said they have real implementations, so we'll see a real live demo of the thing working. So Bob and Koen are proponents of the work, and then we have 3 shorter talks which are kind of by people who are supporting the L4S proposal, but have not been so involved in kind of developing the ideas. So we had Kevin talking about mobile applicability, Ingema, who's looked at some simulations in a 4G context, and Praveen, who's talking about data center TCP evolution, which is a starting point for one of the components. Then we've got a nice slot for open mic discussion about the technology. And then Marcelo, one of the other proponents, is going to describe what work seems to be needed by the IETF. Then another discussion slot about that. And then, as I said, the polls at the end. So are there any agenda bashing or questions, clarifications at this point? Perfect.
So I think you see that we have these 2 discussion slots there, which are lengthy. So I think we want to keep questions during these initial presentations on clarification, right? So if you have a clarification question, you're welcome to come up to the mic. But we want to postpone the discussion on the technology and on the pros and cons to the slot number 7. Because otherwise we're going to run out of time.
Okay, shall I go? Oh, you got a pointer.
Tim Chan, is there a mail list for this activity at all? I don't see anything obvious by looking for L4S mail list.
Yeah, the mailing list at the moment is TCP-Prague. I think, obviously.
So that's a follow-up to the 95 sort of BOFy thing, or meeting. It'd be useful to know where we continue this discussion.
Yeah.
There's no dash, I don't think.
No dash, sorry.
It's TCP Prague without the hyphen.
Yeah. I'll put it in the Jabber room if you want to pick it up from there.
Okay, hi there, I'm Bob Briscoe. This is a talk primarily about the problem statement, which also includes the architecture of the solution. And draft names there, authors are there. And the problem's been described firstly in terms of what is the problem for applications. And it's really that all applications that any user may be using at any one time nowadays tend to want low delay. Like in the past, it was always gaming and voice needed low delay, but even web obviously needs low delay. You've also got all these high bandwidth applications like conversational video, interactive video that we want to move to now. We've got enough bandwidth to do them. Virtual reality, augmented reality, IM, all these things. I mean, delay is probably good enough for those things now, but it certainly isn't good enough for some of the VR stuff and interactive video, particularly where you're also running large amounts of traffic, so it's queuing. And what we want to aim for is something that's an unmanaged service that's for all traffic, like today's best ever internet, but everything's low delay, right? And obviously part of delay is the base delay, the propagation delay, the speed of light delay. And caches where you can help with that sort of thing, but obviously you can't get caches too close to users because then they start losing the probability of hits. So the real problem comes intermittently, and it is only intermittently, where when you've got traffic running at the same time as you're trying to do something low latency, you get queuing. If in the bottleneck, wherever the bottleneck is on your path, assuming two types of traffic are mixing. And even in the case of the high bandwidth ones, you are causing your own delay to your own flow by being high bandwidth. So that, quantifying that, it's roughly double the base delay. You'll end up with queuing. And that's even with a well-tuned AQM, and when you're using the round trip time that it's best tuned for. So that's the application problem. The next problem we have to look at is deployment. And you'll come to see that this L4S solution is based on ECN, and ECN is one of the sort of poster childs for being a huge deployment problem. So I started thinking some years ago that what we need is actually a lot better performance improvement than standard ECN. And that's sort of where this was born from. It needs to be worth, particularly its operators, that won't do this unless they're going to be able to have new products, new services, and there's a really big gain. It's not like 2-3%. It's got to be, hundreds of percent better, right? So that some of these applications we show here, and some of you may have seen the demonstration of the panoramic interactive video where you can scroll it around with your finger and it seems as though it's sticking to your finger. And there's been a demonstration done at an MMSys conference, Multimedia Systems Conference, with all these applications running at the same time for one broadband user. Interactive video, web, gaming, VR, with a 360-degree camera feed from a racing car to a VR helmet, and as you turn your head, a server in the cloud is generating the video for your glasses, but, even though you're running over a broadband network. So there's been some pretty cool demos of L4S. However, what we need to prove in a BOF like this is that we're doing something that can't be done elsewise. So I think I've fairly properly said that access bandwidth on its own isn't enough. You need it, but you also need to address queuing delay. Differentiated services is obviously the IETF solution for low bandwidth, but the point of this is that given at any one time in an access bandwidth, all the traffic may be to one user, DiffServ only gives low delay when you've got some traffic that wants low delay and you've got some other that you can take it from. It's not for all traffic. There are per flow queuing solutions, FQCODL being the main one. But as I said, if you've got a flow in your own queue that's also high bandwidth and wants low latency, that doesn't help you. Per flow queuing doesn't help you, and it also requires layer 4 header processing, and inspection, and a significant level of number of queues, which may be all right in a home gateway, but it's certainly going to be challenging in carrier equipment going in the downstream. So what we do base L4S on is active queue management technology and ECN. And what I'm going to show on the next slide is that although these are on the right track, the root of the problem is beyond controlling the network. The problem is TCP. And you can think of it as TCP is the elephant in the room, which is an English idiom, which means is this huge problem that everyone's just ignoring because it's too big to do anything about. And the problem with TCP is that it's unscalable, and what's been happening over the last few decades, as TCP flows have got faster, the saw teeth have got bigger, and that's why it's unscalable, because the delay varies more and more as those saw teeth go up and down in the queue. And so we're going to call all the TCPs that are friendly with today's standard TCP, which is TCP Reno, we're going to call them classic TCP for the whole L4S effort. That's our sort of terminology definition. And that means cubic, SCTP, quick, anything that's friendly with the existing TCP. So let's explain what I mean by this. Is that one the pointer? Yeah. By this concept that the sawtooth caused the queue to vary. Now, without an active queue management, this picture represents a link and the buffer, and it attempts to represent them in the same space. That obviously one's bandwidth and one's buffering, so they're not really the same thing, but just for the visualization, this queue is filled by TCP because it seeks as much as it can. If you put an AQM in, you can get it to hit the top of the AQM's operating point, so you can get it, so you can get it just about perfect for a particular round trip time, where it will add one round trip of delay every sawtooth, so it will vary between the two. So if you've got a 20 millisecond link to your data center, it will go from 20 to 40 milliseconds. And however, if you try and get rid of that extra 20 milliseconds, you'll cut down into the utilization of the link. So as this one shows, you can get about 75% utilization, and then people start saying, my speed test is not any good. So the point of what we're trying to do here is, and this is the scalable congestion control we're proposing in L4S, has much smaller sawteeth, so the top to the bottom of the sawtooth is much smaller, and also as you go faster it stays the same size. It's scalable. It doesn't just put off the problem, you never get the problem. So then you can have full line utilization and still got the buffer there for any bursts, but generally you keep queuing delay consistently low. All right. Now I've described this as a three factors, because on the left there, I've described the dilemma between queuing delay and underutilization. Also, if you try and push down those sawteeth, TCP will actually push back and increase the loss rate. So you've got a sort of trilemma between three things, but there's also bigger issues that we want to address with L4S that other solutions don't address, and that is that I've mentioned the unscalability of TCPs. You've got the layering violations of flow queuing type solutions, and also round trip time unfairness, which I'm not going to go into, but it will come up later. And L4S solves all these problems, whereas previously TCP, whenever you try and push down on one of them, it just pushes out on another. New word, sex lemma, which is too many lemmas, not too much sex, right? So going back to these fine sawteeth, it's only feasible to have those fine sawteeth if, number one, drop is not used as the congestion signal, because otherwise every top of a sawtooth is a drop, at least one drop. So you just have far too much drop if you try to use that as a congestion signal as well. So you need something like ECN, but obviously not the same as drop. And at the moment, the ECN spec, RFC 3168, says drop must be done at the same time as ECN. So L4S is trying to relax that constraint and say we can have more marking than drop. And the other thing we have to solve if we're going to have these fine sawteeth is this coexistence problem. Here you see a scalable flow and a classic flow, and if the scalable flow has these fine sawteeth to the classic flow, that means there's a lot of congestion because the classic flow expects far fewer sawteeth, so it thinks if there's a lot, there must be a lot of other flows, so it backs off. And it sort of starves itself, and you'll see in the demonstration how that's solved, and I will also describe it in the solution area of this talk. Right, so very high-level summary of this is that classic TCP is the elephant in the room. And this might seem obvious now, but it's not obvious to most people. They think queuing in a queue, you solve that in the network. But there's a limit to that. You have to start attacking this elephant in the room. And that's on the end systems, even though the queuing is in the network. So the next part of the talk is about the solution, and the solution is to build another room without the elephant. That's a very high-level summary. Right. We could stop there and go home, but I'll explain a bit more about that. The other room that you're going to put L4S in, what we do, we put that in another queue. So there's a draft on this called dual queue coupled AQM. And you can think of it like a semi-permeable membrane in biology. It prevents the latency leaking between the two queues, but it still shares the bandwidth. So the sharing of the bandwidth is done by coupling, which I'll explain shortly. And there's three parts to the solution. You need to standardize a classifier, so you know which packets need to go in which queue. You need the queuing structure, and you need the scalable TCP on the sender. And it's the scalable TCP on the sender that gives you the low delay. All the rest of it is just for isolation of old traffic, legacy traffic. Now, if you had to put this in every queue in the internet, I'd probably not even bother coming to the IETF. But you only have to put this where there's likely to be a bottleneck, and most access networks are designed so there's just one bottleneck on the access link. So you put that in the at the entrance to the downlink for the downstream, and you'd get most of the benefit. You get even more benefit if you put it on the entrance to the uplink for upstream traffic. And so going into a bit more detail about this dual queue, the semi-permeable membrane works by coupling the congestion signals that the two queues give to counterbalance the different responses to congestion that the two TCPs give. Now, you might be surprised to see a square root on a slide in an architecture talk, right? You wouldn't normally get into maths in architecture, but it's because the current internet is so dependent on that square root. The whole way TCP works gives your packet rate R is dependent on 1 over the round trip time of the loss rate. And so if we're going to move to a scalable formula which doesn't have that square root, and that's what ensures those sawteeth stay the same size forever, and no matter how fast you go, then what we do is we make sure that the relative dropping rate here and marking rate there have a square relation to counterbalance that square root relation. That turns out to be really easy to do, and Koen's going to show you how to do that, so I won't steal his talk. Now, that looks like it's a mechanism, not an architecture, but actually already we've had different implementations of most parts. The only part you don't need a different implementation for everyone of is the classifier, and we need to standardize that. And we're proposing to standardize that on the one of the ECN code points called ECT1. And that will be your invariant part, but it could be at a lower layer as well and equivalent to IP. The other parts, they all have different implementations. The dual queue has been implemented with a thing called Curvy Red, and also a Pi version called Pi Squared that Koen's going to talk about. There's been 2 different schedulers implemented. This one's called Modified Earliest Deadline First, or Strict Priority, and that deals with overload. Then there are also data center TCP has been used as the primary scalable sender. and there will need to be some safety features added to it, which is going to be talked about at, near the end. There's Matt Mathis's Relentless. Ingemar has at least implemented in simulation a variant of Scream, which is an RMCAP protocol for real-time media, a scalable Scream. So as you can see, it is a container for different solutions. This diagram, it is an architecture, not just a solution. So that's a very high-level summary again. I have to repeat, the classic TCP is the problem. That's the thing we've all been ignoring so far. And the solution is to build another room to put the scalable TCP in and everything else like DNS, VoIP, all the little stuff that can go along with that, and scalable media controls and so on. So that's the end of the talk. Any clarification questions?
While people have clarification questions, we're already going to have Kuhn set up.
Yucheng Chen at Google. For the classifier, do you need to track the per flow state?
No. It's done on the flow will be marking EST1 for the whole flow, and so you're just looking, in fact, at the last bit of the ECN field. That's what you use to classify.
Okay. And then it sounds like since you are already doing this curvy and pi for the classic flows, wouldn't that already change the elephant into a rabbit? That do we still need this DT-TCP solution?
Obviously,
hang on, this is going towards the solution discussion. That's not a clarification question anymore. Could you come back and ask that later?
Okay. Yeah.
Thank you. Yeah. There's another question here.
This is Linda Dunbar from Huawei. I have a question, like, if the network in the middle have a router has a huge buffer, then the packet will be queued there and then delayed. How do you prevent that problem? Do you need middle of the network router to change to support this mechanism?
Yeah, I mean, usually you wouldn't get queuing in a core router. If you do, all that will happen is, at the moment, you'll see some drops and the scalable TCP will just fall back to being Reno. But those situations, from my experience as an operator, you don't want drop in your core, you don't want delay in your core, and normally they're very high-speed interfaces, they have very short queues in time.
Okay, so your bottom line, you're not needing changes in the routers in the core network.
You shouldn't need them. I mean, once you've dealt with your primary bottleneck, which is where a network operator tends to design everything to be at that bottleneck, and they do all their quas there and all the rest of it, then you might want to, in the longer term, you could put a queue like this in because it's fairly simple code, but most core routers, you wouldn't even need it. You don't tend to get queuing there. You tend to push it all to the edge. Yeah.
Thank you.
All right. Okay. Kuhn, you have a demo.
Okay, hello everybody. My name is Koen de Schepper, and I will show you L4S in action. And I have to sit over there because I will use the screen. I don't need. Okay. I'll have to be a little unpolite and sit with my back to you, but okay. So what I'm going to show you is a demonstration, real running code on a test bed with a remote desktop application. So we will remotely log on the desktop on another site where the real code is running, and you will see there a GUI that we use to control real flows and demonstrate and quickly test some things. So what we will do, we will compare Pi, like Bob explained, which is the best we can do. It's the state of the art of controlling in the network the queue, and that's when there is only a single queue and we don't want to inspect further than layer 3 packets. So that's as much as a network can do today, and that means that due to TCP, there will be already some compromises taken depending how big or small you configure that queue. So what we also will, what we will compare it with is the dual pi square solution that we propose in the L4S. And that's actually a dual queue using pi as a classic AQM. And I can announce that we have an open source version of this, which is on this link. You can find it. So you can also experiment with it and validate and even reproduce what I show you here. So we did quite some extensive evaluation of this dual queue mechanism on a real testbed. And there we compared it with many more AQMs and different congestion controls. And so we did, I can show you in the next slide, the testbed. But the main result was that we identified by using data center TCP, which is just as is in Linux today, we identified some safety and in performance improvements, which are needed if we want to use data center TCP as an L4S protocol congestion control in the internet. It could be used in some confined or walled garden solution today, but for the wide internet, it still needs some extra requirements, and that's what we define as a TCP proc requirement. Okay, the next slide, you see the testbed that we used. So it's a real testbed with real equipment. There's a home gateway, there's a DSL modem, a real copper line, a real DSL access multiplexer, service routers, up to a data center. And here is what we call a broadband network gateway, where typically the per user bit rate is limited. So this is actually the bottleneck in a fixed access network. And we deviated the traffic for a set of clients and servers in this data center to an external box where it's a Linux box where we could test the different AQMs. We can configure different rate limits, and we can add some additional round trip time. And then we configure different congestion controls on the different pairs. So this client talks to this server, and this server talks to the other one. And then we could experiment and see what happens. So we will be logging on such this AQM server in such a test bed, and so what we will do is we start some large file copies. We can do that from this server to this computer, and we can also start short web traffic. We do the large file copies to show you what is the rate fairness, and we do the short web traffic to show you what are completion times. So how fast do we get short interactions done on this setup? So you will see at the top, the blue ones, we will typically use data center TCP, and at the bottom of the GUI, you will see some orange. That's the elephant in the room, was also orange, if you remember, like Bob showed. So this will be cubic on, which is a default on Linux computers today. So this box will be then the one where we capture all the traffic and split it again, showing what is the normal, the classic traffic doing in queues, and what is the L4S traffic doing, the blue one. Okay. Okay, this is in the slide deck. You will see that there is some explanation if you want to see what actually it is doing, but I will switch to the demo now. Hopefully everything goes right, because it's a risk. We have two test setups, so I can switch to another one if something goes wrong, but let's keep our fingers crossed that nothing else is happening. Okay, so we start to show the problem with the classic solution. So you see here what's happening in the AQM server, where we can configure the AQM, and you see pi is configured. And then we have the two pairs. This is the blue pair and the orange pair. The orange pair is running cubic. The blue pair, we will be running data center TCP. Here you see in the AQM what are the queues, and it can be one queue, but we separated the packets for the orange one. I will start the flow in the meantime. An orange one, that's cubic. And you see here what Pi is doing. Pi has a target of 20 milliseconds, and he's keeping the average queue size around 20 milliseconds. Okay, you see the link utilization is 100% here. And you also see a drop probability, which is quite low. It's around 0.01, let's say, on average, percent. And you see a little bit of sawtooth because it's wobbling a little bit. This is becoming better. If we have a lot of flows, then we don't have a big sawtooth anymore. We have a little burst in the beginning. That might be annoying for gaming and other low latency interactions, but after a while it gets back to the 20 milliseconds. And you see normal flow fairness is a little bit wobbly. They go up and down because there is not so much feedback. It's only 1%, but actually 1% is 100 times more than the traffic we injected, because we only went from 1 flow to 10 flows. And first problem is that we get 100 times bigger drop probability, which is the square of the drop probability. So if this goes on, and it goes in both directions, there will be more and more drop, or there will be less and less drop, which drastically changes. Okay. What does it mean for dynamic traffic? I will add a lot of short flows. So these are short downloads, 100 per second, and they vary from downloads from 1,000 bytes to 1 megabyte. And here you see the completion time, and because of the buffer, and we have a base round trip time of 7 milliseconds, so there is together, so basically there was only unloaded 7 milliseconds. With that extra queue, there is 27. So our completion times, they vary between, let's say, minimum 27 up to about 100 milliseconds. But because of the drop, it's now around 1.5%. We also get some starting timeouts because the initial messages, or the initial message, the SYN packet gets lost, and we get timeouts of 1 second. Okay. So
a clarification question. Jana Iyengar. What's the second mode there in time? The first one is, you said it's SYN timeout. What's the second one?
The second one are the tail loss, let's say. So when we lose the last packet, then there is a timeout of 200 milliseconds. Okay. So now this is the state of the art. This is the best we can do with changing the network alone. Now there is a solution, and that's called data center TCP. And why aren't we using this today in the internet? Well, let's show you. If we start here, also 10 data center TCPs on a Pi AQM, what's going to happen? It's quite horrible. So we get a big queue, but Pi is good. Its target is 20, so it can reduce the queue to 20 milliseconds, but it increases the drop and the marking probability up to almost 30%, which is, you see what happens on your page downloads times. It's quite horrible. I better switch it off. But also for your normal TCP downloads, these file copies, you get a very small window. So the window of fairness, it's about, well, it almost starves. It's more than 10 times less throughput, up to 40 times less throughput, depending on the settings. So it's not so good. So this is the problem, and we're actually a little bit stuck, unless, of course, we have a solution in L4S, and that's what the dual pi is doing. If we enable the dual Q with pi as a classic, you see we can bring back the classic AQM to the 20 milliseconds, and we get a very tiny queue for the data center TCP, the L4S traffic. So now we have two queues, and we can make the throughput fair. You see they get the same window fairness, and data center TCP has a little bit less wobbling, so that's also an advantage because they get much more signal. They get 60 to 70% marking, so they can be very tied together, coupled. And also here the band, these get less, but they wobble quite a bit. Now the trick to do this is actually quite simple. You see here 60% of marking probability. If you divide it by 2, it's 30%. And then 30% of 30%, so that's a third of 30%. It's around 10% of drop that you have to apply. And if you do this equation consistently, that's the only thing you have to do, divide by 2 and square. And then you get the same window fairness. So, also, to show you that it's not like it's scheduling, it's just coupling based on this queue size, calculate the probability, apply it here, and then do the equation there. You actually make the right feedback to both so that they get the same throughput. And it also is not like scheduling here, because if I change the number of flows here to 4, you see, it still works. It's not depending on the number of flows or of anything. If I only do one flow here, there's also, it goes back to the same window fairness, which is what in the internet today is considered as fair. Now showing the L4S only. Of course, when we run only data center TCP, we can get 100% link utilization with a queue which is on average 0.1%. So it's a tenth of a percent. And we get a 99 percentile of 1 millisecond. So it doesn't matter how much load we do. We can go up to 100% link utilization with a really, really tiny queue here. 99 percentile is about 3, 2, 3, 1 sometimes, so really low. If we add some dynamic traffic, you will see utilization is still very near to 100%. The queue is also very small, around 1 millisecond, maximum 5 milliseconds, 99 percentile. And that's basically because if we are firing a lot of initial windows of 10 packets to this queue, and you see it's not a big problem. And we get really very short completion times. Remember, with the classic, it was around 30. Here we are below 30, below 25 milliseconds. And we get from 7 milliseconds onwards because the latency is very low. Okay. I think that was what I wanted to show you as a demonstrator. Going back to the slides. As a conclusion, I want to say that access technologies, they evolve, obviously. We get higher and higher throughputs, and we can achieve lower and lower latencies, like in 5G, G.fast, which is the DSL follow-ons, or optical GPON, fiber to the home. They all have high throughputs, low latency. And also for Nokia, it's a concern that the classic TCP, when using that, cannot exploit these lower latencies and higher throughputs without at least all the classic compromises. So Nokia believes that L4S is important, and also standardization of L4S is important. Okay, thank you. Any questions?
Any clarification questions while we set up the next talk? Now's your chance.
Maybe for the demo, you want to know?
I think you have a question coming up from over there.
Dave Todd, bufferbloat.net. What was the baseline RTT for this particular demo?
It was 7 milliseconds.
7 milliseconds. Do you have data showing some more longer RTTs, 100 milliseconds or more?
Yes. Yeah, I plan to show it on the live.
I can't hear you.
I plan to show it here, but yes, the utilization. Well, if there is no cross traffic, you can also achieve high throughputs. But of course, like the data center TCP as it is still incremental increase, and it has to be improved. And that's one of the improvements for TCP Prague that we have to do, which are known, so that it gets faster up to speed also for longer round trip times. But it can achieve the 100% utility also for big round trip times. But it takes a bit longer to get to the speed as well still. So.
Okay, thank you.
Yep.
Good. Grab the mic.
Sorry.
All right, we're getting into these shorter 5-minute talks, and afterwards we have the long slot for discussion of the technology.
Okay, Kevin, go. Good, thank you, Lars. So I'm Kevin Smith of Vodafone, and I'm here just to show why we're very supportive of this initiative, and we'd like to see some work going forward. So start just by saying, what's the state of a mobile network today? I think this probably applies across many mobile networks. We see mostly TCP/IP traffic. Now, the volatility that you get in a mobile radio access network can fool TCP into thinking it's seeing congestion when actually it's not. So because of that, many mobile network operators have so-called TCP optimizers, which are split TCP proxies within their network at the moment. And that can reduce end-to-end feedback, causes questions about scalability, etc. The majority of traffic today is encrypted, and any network traffic management methods that we want to look at going forward should not breach privacy. They should be not delving into encrypted content at all, but should be maintaining that privacy. The bulk, well, not the bulk, a third of our traffic by volume is video, and much of this is delivered over adaptive bitrate, which can be very good if you're viewing it as a customer. As you know, it adapts the bitrate according to the signal you're getting. On a mobile network, that signal changes frequently, but it can cause problems because it can seek capacity a bit too quickly, let's say, which can cause problems for other flows. And then finally, it's worth noting that we've talked about QoS. Typically, there's no QoS distinction at the radio layer by the time you get to the masts. Operators tend to run what's called the default bearer for all internet traffic, which means it just gets best effort. So back to Bob's point, what we're trying to do here is kind of make the best effort better, should we say. Okay, so that was today. Going into 5G, these are some of the things we're looking at. 4K video, it's going to be like video, but bigger. More chunks to shift, etc. Okay. Looking at Internet of Things, if you've been following LoWPAN and Core, etc., you know that Internet of Things spans a huge range of applications, from sensors that wake up once every 5 years to deliver a very short report which has to be received, all the way through to lower latency requirements, etc. I think that gazillion figure is an estimate. It may even go as much as a bazillion. We're not sure at the moment, but it's going to be a lot. Ultra low latency services. So the example you've got there is a motorcycle rider. He's got a heads up visor, and it's attempting to inform what's around the corner as reported by other vehicles. So obviously extremely low latency needed for that. And then finally, building out of small cells within cities, things like the 5G millimeter wave, for example, lots of small relay nodes, etc. So all of this in 5G is going to have an impact on traffic shape and network buffering in general. So what benefits do we potentially see from L4S? Well, first of all, it's transport layer independent, which is great because as we're seeing the rise of quick over UDP, for example, we don't want to be looking at something which just handles, for example, TCP. It doesn't breach encryption, again, because it happens at a different layer. So I keep moving in and out of the mic's focus, that's better. It doesn't breach encryption, which, as I mentioned, is something very important. As we build out capacity for 5G, that in and of itself doesn't solve latency. So it's important that we have something which is draining the queues quickly to improve latency. As mentioned, we are looking at a blend of traffic, not just ultra low latency traffic, but traffic which doesn't really require a latency sensitive application, let's say. But the fact that, as Kuhn showed, it can coexist with other kinds of traffic, that's very important. This one, I don't want to dive into this rat hole, but I'm involved quite closely with net neutrality discussions. And something which gives delay, low delay for all is a lot easier than saying, well, here's something which gives good service for some but not others. So it ticks that box. A couple of the question marks, ECN is not widely utilized today, but of course this could encourage its use, so maybe that's not so much of a problem. We would, you know, as due diligence, we would look to run trials within the mobile network on FQ, CODL, etc., on mobile access networks, just to compare and contrast, but that makes sense. And then finally, potential for L4S to optimize the buffering at the radio layer, which has been a historical problem. We'll just go into that quickly. So, big buffers, good and bad. On a radio network, when you've invested in spectrum, what you do is you chop up that spectrum into frequency and time blocks, and you have those ready and available for any devices connecting to your radio network. So what you want to do to make the return on your investment is make sure that that radio is always being used, it's efficiently being used. So the buffers are there to make sure you've always got stuff to inject into the radio modulators. Buffers can also account for volatility in bandwidth. As mentioned, the signal can fade, you can walk behind a tree, you get interference, etc. So having stuff buffered up makes sense for that. And it's, you know, big buffers are good for bursts as long as the space is available. But of course, as we've seen, it can impact TCP congestion control and flow control. It's not maybe delivering the true picture of what's happening to the flow. It can reduce throughput. And the bigger the buffer, the more chance of packet loss at handover. So if we're seeing a huge potential rise in the volume of traffic, something which drains the queues quicker can be very attractive. So this here is me being all really highly optimistic about everything. Something which can empty queues quickly, leaving room for bursts and with low loss for all traffic is hugely attractive. Ingemar will, I believe, have some basic test results for 4G networks, which we can see. But that's me. Any questions for clarification?
And Ingemar, you can already come up. You're next.
Cool.
All right, great.
So Ingemar and Praveen, we're a bit behind schedule, so can you be as
Excuse
quick
me?
as you can? We're behind schedule, can you be as quick as you can?
Go fast.
Go fast.
I will go through and show, motivate why we are interested in this topic, and that's this one. And I don't believe I need to repeat the benefit with the mix of long and short flows that Kevin already outlined. And maybe add that you are already in 5G you will have multiple beams technology and all other stuff that can make throughput quite variant. And also, if you look at these cell phones around the units in this picture, it doesn't need to be cell phones. It could be home gateways as well. And meaning that you can multiple users can be behind one home gateway, and then you share one bearer. And that's also increased the benefit with having short queuing delays. And this, to sort of visualize this, some early simulation examples, sort of based on maybe count hours or days, sort of, and also elaborate tuning of queue marking algorithms and that stuff. And what it shows some examples what you can expect as a sort of a worst case. I would believe there is probably a lot of improvement potential here, and what we have seen is that it's promising technology, and you can all of the initial results show that you can get both high throughput and low latency. First, we have this simple comparison where you compare cubic with classic ECN against data center TCP with L4S, and this is sort of just one user in a 21 cell deployment simulation, and you can see that if you use data center TCP, you get away with much lower queuing delay, as when you look at upper graphs compare, and much more stable congestion window evaluation as promised, and still almost the same throughput. And sort of a good thing. And if you increase the load, you can see that you get less variant queuing delay, and that's also a sort of a benefit. And we are able to drain your queues quickly if you encounter more users in the cell or an additional load in the network. That's also, and then did some experiments with the Scream, which is the congestion control algorithm for WebRTC candidate. And currently it relies on packet loss and delay as congestion signals. And packet loss is not decided if you deal with video, because then you need forward correction or free transmit to improve the quality of the video. And delay is not a clear congestion indicator actually in a 4G context, because you can have additional delay spike during handover and that stuff. So it's not optimal to use delay. But on the hand, if you use ECN, you get a clear congestion indicator. And if you compare the lower graph, you have packet delay and video frame delays, and compare it with ECN, you get, depending on how you tune the sort of a classic ECN algorithm, you get somewhat lower queuing delays or IP packet delays. Whereas if you run with L4S ECN here, you can get a much larger improvement actually. And what the jitter you see here is actually the scheduling jitter, and that is mainly so because of I run with LTE simulations, and 5G you can get away with shorter HARC round trip times and shorter TTIs, and possibly you can reduce this jitter spikes also. That's about it.
Great. Questions while we bring up Praveen? And thanks for bringing us closer to being back on time.
Hello, everyone. I'm going to talk about data center TCP evolution today. So just a quick recap of data center TCP. It's a variant of TCP intended for deployment in data centers. So I'll give you a bit of history about it. Analysis of data center traffic shows that there's a mix of short flows and high throughput long flows, long duration. There is also map-reduced type of workloads where you fan out work to a bunch of servers and they all fan in at the same time, and that causes shallow buffers and commodity switches to overflow, and that causes tail drop, which is bad for classic TCP. So the solution was to use ECN in a modified way, which requires changes on both the TCP sender as well as receiver, and it also requires middle boxes like switches and routers to cooperate. The key idea is to, instead of using a single bit feedback, convert ECN to a multi-bit feedback. This is done by changing the receiver to mark packets which are marked as congested by the switch, and then the sender reacts based on the proportion of packets that were marked. DC-TCP requires configuration of switches to set a marking threshold. Most of the data center switches used in data centers do support this type of configuration. As I said earlier, it's only recommended to be deployed in a single administrative domain where you control both the sender and the receiver as well as the switches. There's an informational draft RFC in TCPM. Actually, the version number is wrong. We just updated it yesterday, so the version is 02. please feel free to check it out and give us any feedback. So the key problem today is that data center TCP and classic TCP cannot share a single bottleneck link. The intuition behind this is that once you set a very low marking threshold, the switches will drop packets that are not marked with ECT. So classic TCP will start hitting packet losses and it will scale back a lot, allowing data center TCP to kind of, take over the link. So as was mentioned in some of the previous talks, data center TCP is a great choice for a scalable congestion control. Most of the experiments have been done with TCP at this point. It's a great starting point because there's multiple implementations. So Windows Server has supported this since 2012. There's now an implementation in the Linux kernel as well as FreeBSD. And it's also available, from IPR point of view, it's available royalty-free and non-discriminatory for all implementers. Experiments show that this can work over large RTTs and also deliver both low latency as well as high throughput. But for safe deployment over the internet, you need two things. As Bob explained, you first need a segregation of classic TCP and scalable TCP, as well as TCP prog. So TCP prog is essentially what you can think of as DCTCP++, like what changes would be needed to DCTCP to safely deploy it on the internet, which I'll talk about in the next slide. The name data center TCP is not, it becomes a misnomer once you kind of want to deploy it on the internet, hence the change in name. So this is a subset of the requirements. Marcelo is going to give another talk after this, which will list all of the requirements. This is just a subset and some initial thoughts on, it's basically on each of these. So the very first step is you need a way to identify, because you want to segregate this traffic, you need a way to identify scalable traffic versus the classic traffic. And ECT1 seems like the most reasonable option that we have. Again, subsequent talks will cover more details on this. Currently, DCTCP lacks any kind of negotiation mechanism. So the way this works in Windows Server today is it's a heuristic. So if the RTT is less than 10 milliseconds and ECN is successfully negotiated, then the implementation automatically picks data center TCP as the congestion control algorithm. But obviously, this can lead to problems if you're deploying this on the internet. You do need an explicit negotiation scheme. There's the accurate ECN draft, which has an essential part which solves the negotiation problem, and that does not require a new TCP option. So it seems like the most safe option that would give us negotiation.
Praveen, can we move to your next slide? We're running kind of out of time.
Okay. Yeah, so if you have questions about any of the remaining ones here, please let me know and I'll be happy to answer. So experimentation enablement, Windows Server already supports this out of box by default. There's also a bunch of configuration options where you can force this for all connections. For client operating systems, there's an undocumented socket option that you can use to start testing this with even Windows clients. Microsoft is very interested in this effort on both deployment of ECN on the internet as well as L4S. Thank you.
Thank you. So we have pretty much exactly an hour left and an hour and 10 minutes of material. So we are a little bit short on time. This is now the slot for discussion about the technology. So anybody who, like Yusheng, I told earlier to sit down and wait, now would be the time to come and ask general questions about the technology. So everything you've heard until now. After that discussion slot, we have a short presentation by Marcelo about how the IETF could structure this work, followed by another discussion section on, what should the IETF do? But this is now about the technology. Bob, you're going to ask a question for yourself, or you're just waiting in anticipation? Or
in case Yucheng wants to ask his question. Yeah.
So let me repeat my question. Yucheng Chen here. So I think the dual queue shows that we will use the curvy red and pi. And to me, it sounds like the elephant will be turned into rabbit in this case. So do we still need the DC TCP part of the solution?
Yeah. So I think Kuhn has shown that your rabbit is, with a good AQM, when you don't have to go into layer 4, you're talking about 20 millisecond delay still per round. So what we're trying to do is, as I said, enable new applications like the ones we've seen with VR and things like that, so that operators think this is cool enough to want to invest in or get their equipment vendors to invest in putting this into their networks. So we want to go really low.
But would that be just a tuning of the pi algorithm to further tune down the target?
No, because as I showed, if you tune down the target, if you continue to use TCP, you lose your utilization. That's because of the big saw teeth. And so people aren't going to want to do that. They're going to look at speedtest.net and say, hey, look, I'm getting 80% of what you've sold me on my line, right?
Okay, Ati, thank you.
Yep.
Magnus Westlund. So how well is this tested with real-time media and higher bit rates? Because, I mean, I see some potential for having interactions between the kind of adaptation intervals, etc., like video frames, etc., and how you get the feedback. So it would be good to see. Well,
well, the best way to do this would be somebody could answer the question. I don't know who that would be. It might be Ingemar. Everybody from the proponents, yeah. Why don't we do it this way? Everybody who spoke up here, come back up here, and then
so maybe
pick the questions as they come.
Yeah, maybe I can answer the question. Nobody's listening.
Hello, Ericsson. Can we participate in the discussion?
You're getting an answer.
Or
okay.
Who's up next?
So maybe I can answer the question also. Your concern is about rapid changing throughput. And so with L4S, we can guarantee low latency, but the throughput might vary. But of course, there must be enough throughput for your application to be able to do that, or you have to have a very fast adapting application. And that's a possibility that is now, it's kind of paradigm shift that you can make your applications innovate on having very fast adaptations and give a good user
I think that's fine with my question is primarily around the congestion signal, how well it interacts with that intervals that you kind of sending out packets every some intervals, and you're gonna get, which is different from, for example, what TCP connection would do.
So the good thing about this is also that it allows bursts to exist because they're sent at line rate. So I didn't show it, but like these for initial windows, if you would use a network scheduling like FQ, they would have to wait their turn, and a big burst will be scheduled slowly. In this case, you share the bandwidth, and everybody can burst at the highest link rate. So it depends also on how the network is built, let's say. Okay.
But we're gonna try and keep it short, and we're gonna do a dual queue approach over there.
Usually I prefer 1024 queues. Dave Todd, bufferbloat.net. I know this is a new audience, and I wanted to point out that this work is an outgrowth of many years of work on the behalf of Bob Briscoe, as well as many years, and all this other group, as well as the AQM working group. And the fact that AQM as we built it today, is vastly superior to what we have deployed in the field is my first takeaway. Please consider these technologies as we've already defined them. The next step is what they're attempting to do with this stuff today. And my question and my point, unfortunately, is that I personally would find your demos far more convincing if you would put them head to head against flow QCODL.
I could show you, and I could show you the differences also. Well, the main difference is that FQ tries to solve the problem in the network, and L4S tries to solve the problem in the endpoints. Okay, and it has some consequences because in the networks you don't know everything, you need to know everything, and
Again, it is a difference in approach, and that merely the fair queuing stuff, it ensures zero latency or near zero latency for many forms of traffic. But again, the point is trying to get that first step happening.
Can you prepare a demo and we'll give you 2 minutes in a while to answer that? No, not now. Let him set it up first. Let's keep going with the questions.
Matt Ford. I think the last presentation got into this a bit, but then it kind of got moved. You moved on, and I kind of missed the point. How does the end system know that it's on a network with a dual queue coupled AQM gateway?
The endpoint doesn't, right? So the endpoint basically just negotiates ECN and basically using accurate ECN. So, yeah, you want to?
Yeah. So if it's not on a network with a dual queue, if it gets a loss, DC-TCP just reverts to Reno behavior, right? If at some future point before we have L4S, anyone actually does deploy ECN in the network as a classic ECN, then the end system would see a delay before it sees the ECN, whereas with L4S it wouldn't. And so it would be a similar trick to what's done in compound TCP, which is also Microsoft, where it then would sense that and behave like Reno rather than the other. But that's not been implemented yet. That's arm waving, right?
Okay, you should.
I was just going to follow up that similar question. I think it would be nice to see sort of what's the incremental deployment plan? What are the requirements and dependencies? Should we change the router to L4S before we can upgrade the stack, or all this can be done in a synchronous manner or something like that?
So the idea is it can be done in parallel, and it can be also gradually be exploited. So we have data center TCP as it exists today in Linux and in Windows, and we could build some business cases around that by only changing the network and have kind of walled garden. In the meantime, when the equipment is there, it can be used for the public internet as well. It's just reconfiguration, and TCP Prague, which is work that has to be done to make normal TCP. It's an add-on to normal TCP or an add-on to data center TCP to cover all the fallback mechanisms, and we have ideas about that. So like Bob explained, if the delay becomes too big, it's definitely not TCP Prague, but then you have to fall back to Reno. If you get no marking but drop off, obviously you have to behave like Reno. So you can make a TCP which works perfectly on both worlds. And then when there is a bottleneck and there is the L4S dual queue implemented in there, you get the benefits. So they can be in parallel deployed.
Okay, I think I got the rough answer I'm looking for, but is that part documented anywhere in any of this draft?
Yeah. So in the L4S identifier draft, there's the requirements for that. But I mean, in DC-TCP today, I mean, if it wasn't clear what I said, DC-TCP today does that fallback. It's already there. The bit I said is arm waving is fallback if there's ECN in the network, but it's not L4S ECN. But the fallback on loss is already there, and it's in Linux. There was a bug in the Linux one which Kuhn has fixed. So you know, what's there today already does the incremental deployment both ways. That is, whether the network or the end system does it first, it all works.
Okay, so you said the detail are already there in the draft you mentioned. Okay, thank you.
Pat.
Pat Taylor, Broadcom. A couple of the presentations talked a lot about carrier, so I want to make sure that the intent here is to cover data center as well as carrier, and that's part of the scalability.
Sorry, I keep jumping up. Bob Briscoe. The original reason I was doing this when I was in BT, I'm now in Simula, was because we had data centers on BT's finance networks where it ran the network for hundreds of finance data centers, and we couldn't deploy data center TCP because there was too many administrators. You couldn't sort of get it all done on one day. So we were doing this for the data center environment, but what we've shown today is more for the public internet, but certainly it could well be first deployed in a data center environment. And if you put this where the congestion is, or the bottleneck is likely to be on the Tor switches, and that I've been looking into how you would do that for the dual queue, then you would have a solution for data centers, for multi-tenant data centers where you can't control everyone. Some are using old TCP, some are using new for inter-data center work, and so on. Yeah.
Right. Well, and there's applications that care a lot about the low loss, low latency, and other applications where people don't necessarily care about implementing that.
David?
David Black as an individual. So we've got the dual queue sets up a low occupancy, low latency queue and a high occupancy, high latency queue, and relies on only scalable senders using a low occupancy queue. Where are the incentives in the ecosystem you're talking about to keep the non-scalable senders out of the low latency queue?
It's a misunderstanding.
Okay.
Should I? Yeah. There is no, you've misunderstood. All the large flows can also be in the L4S queue. That wasn't the purpose of the demonstration. Wasn't to say this is like diff-serve where you've got to have the.
No. Here, Bob. Question is as follows. Doing a little more precisely, as you set things up, only your scalable sender, your data center TCP, will set ECT1 and get your low occupancy, low latency queue at the bottleneck. Everybody else is not supposed to set ECT1 and go to the dimensional queue. Where is the incentive for everybody else to not set ECT1?
It's the same as today by not responding to congestion. And the advantage of the dual queue is that it also behaves in the same way as a single queue today. So it doesn't protect you and it allows like it is today. So you can have ECT1 in the queue and have some rate limiting or some alternative mechanisms that that push away other traffic. That's still possible, but so it's not solving that and it's not preventing that as well.
I think the good question is can somebody who's misbehaving destroy the scheme for everybody?
Yeah, so as the demo showed, actually, if the classic TCP tries to mark ECT1 and goes on the other queue, then it will completely suffer because it wouldn't be able to, it will react badly to loss because that queue will drop early.
Okay, that takes your price, BT. And I think in general, the point I simply want to make here, we don't necessarily have to have a good answer for it. We need to understand that there is some degree of trust that ECT1 is set correctly on all traffic. And if ECT1 is not set in the way you're assuming it, or is dramatically not set in the way you're assuming it, your dual queues are going to dramatically not behave accordingly.
Yeah, and I've said in the security considerations of the problem statement that if that trust is okay, then we're fine. But if we find that there are attacks, we might have to detect those attacks and detect the behavior that's causing large delay, large spikes of delay in the queue and do something about it. But we'll have to see whether that happens first. And the incentives seem not to be for that.
Jana.
Jana Iyengar. Some of the questions I was going to ask have been asked already and have been answered, but carrying on this last thread, I think I don't know if it's a security consideration, because it really is that if there's an attacker, so to speak, then you basically, an attacker that's not an accidental TCP sender, it just happens to mark ECT1. In this case, it's a deliberate marking of ECT1 so as to use the low latency queue. Then you basically are no longer a low latency queue.
right? I mean, I don't know if it's a security concern.
But I think it's the same problem as today. If you have a PI congestion control, what happens if you just push in traffic? You just increase the drop rate. And if you don't have PI, you just increase the queue. So it's exactly with dual queue. If there is somebody who fills the queue, it fills the queue, and then it's up to the AQM to decide what will I do? Allow a big queue also in L4S, or start dropping packets in L4S. I mean, there's nothing changed, and we need other mechanisms to prevent attacks. It's not the role of an AQM, right?
Yeah, fair enough. So the question I had was, and I haven't thought about this long enough, so the answer may be just very straightforward. We're just winding up the AQM working group, and we have a whole bunch of stuff that we're trying to recommend that the same people that are being targeted in this work do. So what do you think what do you think our recommendation will be with the L4S stuff? If we want to make a recommendation to them, do we wait for them to deploy AQM first? Do we say, hold off, we're going to come up with something more? Or how are we exactly going about this right now?
Can you hold that question until the second discussion,
The
Steve, which is
process,
more about
I wasn't sure if
what IETF is
I
doing.
I can answer it very quickly.
No,
We're
I don't
not
want you to.
saying
No,
don't deploy AQM now. You know, deploy AQM now. Do what David.
You're not quick.
Just said.
Roland.
Roland Blesk, KIT. One observation, yeah. AQMs can achieve good utilization and low delay if you have multiple or many flows. For only a few flows, you have to change TCP. That is more or less also can be confirmed from our observations. But one concern that I have is the dual queue fixes more or less the, let's say, strategy by a queue coupling. So if you change the congestion control behavior at the endpoints, maybe you have to change the queue coupling principle too, and that's maybe not so good, right?
That's something we have to decide. So in TCP Prague, how TCP Prague should be scalable and future safe. And then we decide a coupling. And of course, if the classic TCP evolves further, the coupling might also to be evolved, but well.
Yeah, but you have to change it in the gear, and that's, I mean, at the endpoints, you're far more flexible in adapting your congestion control strategy. But if it's now tied to what's the queue coupling doing, then
there is not much like feedback or coupling you can have to make it scalable. And so, okay, we can do pretty good with a certain assumption, and we can improve TCP features very well when doing that. So
I'm going to close the queues now. So everybody who's standing now, please ask your questions. Christian.
Okay, first I'd like to make a comment. I mean, there is a lot of discussion about the relation between doing this ECN feedback and the 2Q solution and the FQ PI or FQ coder kind of solution, which do flow isolation as part of the AQM. These are not, I mean, it's a tension that can be resolved, because if there is flow isolation, then each flow can have its own feedback mechanism and drive to the results we want. So flow isolation is not in itself contradictory with what we want to do. And in fact, if you look at what you are doing, you're specifying a different feedback mechanism for the network. Basically, what you are saying is, hey, network, please warn me very quickly if the queue is going up. And that mechanism by itself, if it is elective, is a very nice mechanism. And regardless of whether you do the coupling or whatever, I actually have a lot of reservation about embedding these square root formulas in the coupling, because frankly, it's a hack. First, TCP is not square root. I mean, your average TCP connection sends as many packets in slow start as it sends in congestion control. Many only do slow start. In that case, they are not bound by the square root formula. So something different there.
There is also a difference in dynamics because a lot of slow start or small flows don't get any feedback at all. So it's only for the long flows that we need some fairness, because if you do a big file download, if you do a speed test, it's that is going to be tested. If you have a short round trip time, you can respond very fast and do things quick. If you have a long round trip time, it takes more time before you can respond. But at the end, we want to have some fairness between those two. So we focus for the long flows for throughput fairness, and then we have another equation or another mechanism, dynamic mechanism for the short flows, which I agree is not following the square root.
If I look at my telemetry, I see that there's only a very, very small fraction of the flows that are anywhere close to being long flows.
Yes, but I mean, we test a lot of throughput, and if we do a big file download, if we want to have video quality performance, and video and big flows will be more and more introduced in the future, it's about throughput and low latency if it's interactive. If we have virtual reality video, it's big throughput and small low latency. Okay.
Don't get me wrong. I love the idea that we have to solve for low latency. I'm just saying, hey, we have to be careful not to do hacks. We have to be careful not to do things like that.
And I agree with you. It is worrying having to put a formula into an architecture, but I just wanted to make it clear that there are opportunities for short flows here as well that we haven't even started to exploit, but it's something I can see in the future. Having a very shallow threshold on the ECN, on the L4S side, means you can start testing the capacity of the network much more quickly and much more explicitly to get your short flows starting much faster. But we haven't even gone there yet, but that will be the next thing.
Please be brief in the questions and even briefer in the answers.
Hi, Colin Perkins. Coming back to the question of incentives that I think David Black mentioned earlier. I think you have a very good story for why you wouldn't take a standard TCP, a classic TCP, and mark it as ECT1 to try and get into the short queue. I think, on the other hand, though, there is a very strong incentive if I'm building a non-TCP application to an interactive conferencing application, for example, to mark my traffic as ECT1, shape it, and not do congestion control, so I get into this queue. And the incentives which would break a TCP flow and stop you doing that don't appear to apply in that case. So I think that's something that you should consider.
But that's what we want. We want those flows in the L4S.
But in a responsive way.
Yeah. Well, it depends whether it's unresponsive forever or just less responsive than TCP.
Yes, but if I'm building a non-congestion controlled, non-adaptive video sender, I want low latency. I would set ECT1 to take advantage of your scheme.
Yeah.
And there is an incentive to do that.
Yeah. And
completely ignore the CE feedback.
And I mean, Koen's done experiments with this, and yes, you can effectively create a case where you push all the TCP traffic to use the remaining capacity that you're not using, and as long as you're not more than the capacity, that's sort of what some people want. Now, whether that's what the IETF wants, I don't, it is a different matter. But if this thing moves to loss, then it's got to self-control itself. Otherwise, it's hurting itself as well. So it does depend how you look at this. But in general, that problem's the same as what we've got now.
We have to define overload mechanisms, which are, of course, not worse as we have today. If today somebody sends non-congestion controlled traffic more than the bottleneck, we get a big drop or a big queue, and that's the same what we can do today. That's with L4S. There is not really a benefit or a bigger disadvantage with L4S than there is today already.
I think that the disadvantage is that you're pushing the TCP flows out of the way a lot quicker.
Today as well. If you use SPI, you're pushing away all the traffic.
But the queues, because the queues are smaller, you have a bigger effect with
Not necessary, because you can allow the queue to be bigger than they are, or it doesn't change a thing.
Okay, usual.
So we have compared ECN and loss-based condition control. So what about delay-based?
Yeah, there is some discussion ongoing about delay-based or not. We didn't evaluate delay-based because they're hard to coexist with drop-based, and also for fairness, I don't know how to solve that.
But if we can have a separate queue, can we have a separate queue for delay-based and we don't have ECT issues, something like that?
But there, the conversions to fairness and things like that are different. I don't know.
Yeah. I was just going to say, if you manage to get an operator to change something in their network, I want them to change something in the right way quickly, rather than say, oh, okay, we're going to change it all, but we're just going to make you infer what's going on because we're not going to tell you, or you can have ECN. Which do you want? You know, you've got this operator to actually do something, and then they don't do anything. Why do you want to do that?
So I take your answer that you think ECN is a more straightforward approach.
I've just come back from a workshop where we had a discussion, actually an argument between Microsoft and Google about this for data center environments. And if delay is the problem, measuring delay to try and minimize the problem doesn't help you when you're trying to get it to zero, because then you haven't got any delay to control your system. Whereas if you have ECN, you can control it even without any delay.
And I think the combination can be used as well, because delay is important also for fallback mechanisms and maybe to improve the ECN feedback.
So I don't necessarily want to go into the loss versus delay here, because that's not part of what the BOF was about. And we do need to move on because we're running a little bit late. So Jana, can you be fast? And Christian, we saw that you tried to sneak into line. Don't. We see everything up here.
Jana, Inga, I was actually going to ask something along similar lines, but I won't say delay-based. So don't shoot me yet. The model here, and I want to make sure that we are on the same page as far as the model that's being proposed here, right? The model that's being proposed here is that there's a separation of queues at bottleneck routers, at bottleneck boxes, and there will be two separate queues. One of them will be considered to be the low latency queue, but that is effectively going to be marking ECN bits. That's DC-TCP style marking. That's one part of the equation. The sender response to that is the second part of the equation. Now I can imagine cases where a sender looks at this and reads delay signals instead of reading the ECN bits and responds to that, because this is a low variance queue. And it is possible for the sender to also do things of that sort. I don't think you've evaluated that, but I wonder if it's worthwhile separating these two concerns and trying to evaluate TCP Prague as one of these solutions in that space.
No, I don't see anybody going to the microphone, so you're not going to get an answer. We do need to move on because we're now quite far behind.
How are the blue sheets doing? Blue sheets, where have they got to?
Disappeared.
They've disappeared at the
No, there's
back?
one back there.
Has anybody not signed the blue sheet? There's a couple right at the back, and there's a couple over there. Can you send them in the right direction? Thank you.
Marcelo, we know that you're good at talking fast, so make us some time.
So just a sec. So there was a question about FQ CODL comparison. So if you're interested in the answer to that, come and see Kuhn at the end. He can answer that question. And I think Dave just left the room, so we'll have to make sure he knows. Marcelo.
Okay. So what I'm going to present here is basically a summary of all the work items that are needed in order to accomplish L4S. Next slide. So during Bob's presentation, basically he described that there are three types of components that are needed for L4S. One being the protocol to distinguish the type of traffic to inform the classifier, the network component, meaning the dual queue, and the scalable sender, so changes to the endpoint. Next slide. So basically here I compile all the different work items that are needed, classified based on these three types of components that we need to work on. So the first deliverable would be something like, the first work item would be an architecture. So this L4S system has a lot of components. They need to work coherently. So we need some kind of document that describes how the whole thing works. Then on terms of the protocol, so we need two things. We need on one hand the identifier to enable packets to be distinguished in which queue they need to go. And then we need to update RFC 3168 to explain that an ECN mark is different from a lost in this context. In terms of the network, we need the dual queue AQM. And in terms of the host of the scalable sender, we have two types of items here. The ones that are in blue, the are ones that are needed for this to work. And the ones that are in gray are performance optimizations. Right, so in order for this to work, from the endpoint perspective, we need the scalable ECN feedback. We need to be able to fall back to TCP on loss or when there is an classic ECN bottleneck detected. We need to reduce our round trip time dependence. That basically means that we need to avoid that flows with very short round trip times starve flows with longer round trip times, especially when we are enabling very low round trip times on the global internet. And then we also need to be able to scale, to have congestion windows that are smaller than 1 maximum segment size in order to be able to deal with very low round trip times that will be enabled by this. In terms of optimizations, we need to be able to mark ECT marking of TCP control packets. We need faster than additive increase, and we need faster conversion to fairness in this scalable transport. So the other thing that I list in here is different starting points. Not all of these things need to be different documents. Not all of these need to be different RFCs. Maybe some of these that go into existing RFCs. But in many of these cases, we already have some starting point or some document describing them, and that's what I include in here, just to show what type of work has been going so far. So this is to give you a rough idea of the amount of work that is required in order to accomplish this. It may look like a bit, like quite a bit, but as you can see, there are a bunch of things that are already going on, and there are a bunch of things that will actually happen irrespectively of L4S because are needed in general and not specifically for this effort. Yes.
Hi, Colin Perkins. So it does look like a reasonable amount of work. I think you're missing some significant components.
Okay.
You only mentioned TCP and the IP response. You say nothing about the non-TCP congestion control that will also need to be updated.
Yeah, well, there are some things referenced there that talk to some other transport. I personally, that's my own opinion, we think we should focus on TCP to start with, focus on TCP and DC-TCP, just to start with that. That will my take, but.
So the reason I point this out is that there are existing RFCs for the use of ECN with non-TCP transports, which you are violating musts in.
Yes, and we are violating. Sorry, and we are violating the must for TCP as well. So that's what I'm saying needs to be changed.
Right, but my point is, if you're going to change it for one, you need to change it for everything that uses ECN.
No, because I think just updating 3168 in general for all. In general.
No, it's not sufficient.
Sorry.
Can I finish?
Yeah. So in case there was any doubt, we are starting the question section on what.
My point is that RFC 3168 says the general ECN response and how TCP should respond.
Mhm.
There are other RFCs that say the same sort of response has to happen for other protocols. And if you're updating that response, the response at the IP level,
Right.
then you also need to do that for everything else that uses ECN. But that's not what's written in the RFCs now.
Can I cut this short, because we've just written text that should be produced tonight that says exactly what you want to do. So it should get submitted tonight.
Yeah.
It's not on that list, I admit, but we've already done it.
It's not on that list, but that list is also missing things like all the work that has to happen with the circuit breakers in AVT and in TSV, and with the updates to the RMCAT group and so on. So it's not just it's not just one paragraph in one draft to say that it also updates this other RFC.
What we've done so far is update existing RFCs. If there's ongoing work, then the authors of that work can take account of that.
No.
Yeah.
You're changing things underneath them, and it's up to,
I would like to add that some of those changes are actually independent of L4S. It's something we want to change anyway because we know it's wrong. It's ongoing work we are doing anyway.
Correct. Corey.
Wow, what a lot of comments. Yeah, there's a bunch of those that are RFCs. They're not just work, and they're deployed, and people are thinking about them, and there's other working groups working on this. So there's other areas of the IETF that will be impacted.
Go ahead. Can I just answer Corey's point? I checked certainly with RTP over ECN and RTP over UDP, and as far as anyone could tell on the mailing list, no one is using ECT1 for that. They're only using ECT0. So if we change the RFCs, it would just be a change to the RFC, not to any implementation.
But the point is this affects existing work, and you need to change that work. We need to go through and change all that work, and that's not listed on your list of work items.
Okay. Well added.
Yeah, it's just add to the list, Bob.
I just wanted to make, my name's Tim Shepard. I was gonna just leave this until Lars said, because you're changing things underneath them, they're going to have to. But if they don't switch from ECT0 to ECT1, you're not changing anything underneath them. And they could just remain as things are now, right?
I think underneath was the wrong words. So
Yes.
a definition is being changed that has been incorporated into other RFCs. So at the very least, we need to check that making the change doesn't break anything else.
For ECT1? I don't...
For both. So
what changes for ECT0? I don't think anything...
So we've already had one draft got to discuss at the IESG level, which...
Colin, can you go a bit closer?
So we've already had one draft which was in IESG review and got to discuss based on this, which says nothing about ECT1. So this is impacting other drafts which use ECN, even if they say nothing about which ECN marking they use.
So I think the point that Colin is raising is that the proponents of the work need to double check what other work has already been standardized that uses ECN and what other work is currently going on, and that list might not be complete.
Yes,
that is the point, right?
Yes, I'm not disagreeing that this work is valuable. I'm saying that it has much wider impact than the proponents seem to be saying, and they need to look at this broader impact.
Okay.
Mia Kulevin again. So there is other work ongoing in TSV working group to change the reaction to ECN that is independent of this work. So the changes you're talking about need to be done anyway. It's completely independent of L4S. We will do them.
Yeah, basically, Mireia is right there. We want to have a way to signal that we want high volume feedback from the network. Regardless of whether we do TCP Prague or something else, having an option to elicit high volume feedback from the network is a good thing. Okay, so yes, sure. As a deliverable, you're right. We need to do the list of everything that's impacted and do a checklist that they are in fact using ECT0 and things like that. Yes.
And this is all.
Yeah.
And this is all I said. But the people who, we keep hearing people saying, we'll do this in TSV, but it's a much broader issue than doing it in TSV. It impacts many more working groups than that. So it's not just a case of we're doing this work in TSV and the problem is solved. It's not, it's much broader than a TSV problem.
No, I think what Mirja is saying is that, so this is not something that will become a problem because of L4S. This is already something that the TSV folks that are doing this work over there need to take into account now. David.
Again, my point is it's not just a TSV WG issue. It's a much broader issue.
Correct. It's not an issue. The issue is that the folks who are doing the work in TSV WG should think about the implication that what they're doing there has elsewhere. Correct? Okay. Great. David.
David Black, trying to speak very carefully as both a TSVWG chair and an author of 3168. So I basically agree with Colin, and to some extent had a related private discussion with Marcel this morning that I'm going to try to share, hopefully non-controversial. I do like what I see here. I do like the ideas being pursued, and I think degree of experimentation is clearly called for. And to the extent that RFC 3168 prohibits experimentation, we have a problem. What I believe is going to happen in TSVWG is there was at one point a draft that proposed to actually change the reaction to ECN. I think that's now being split into two drafts. There will be a draft talked about in TSVWG whose goal is to figure out what do we need to do to open up this area of 3168 prohibitions to allow this experimentation. And a key issue I'd very much like to hear discussion on TSVWG is basically what Colin was asking, although I'll say in different form. When we if we open this up to experimentation, we're tinkering with things that could break the internet. What are the appropriate level of controls over the experimentation that will allow this kind of productive work to proceed responsibly without raising the risks of breaking the internet? So I think we're going to do a process-oriented draft in TSVWG to try to figure that out and try not to sandwich it with the other drafts that have particular content proposals for what should change.
Magnus Westland. What I reacted a little bit is very certain that, oh, everything uses ECT0 and we can use ECT1 to be marking this. It feels a little bit too certain in some cases in this discussion. I mean, there's nothing today in the existing specification that doesn't allow you to use ECT1, etc. There's some, in certain cases, recommendations, which has been good, for example, around RTP for the specification that we know uses that. I don't know if there's unknown usage, for example, for ECN or for RTP or UDP, which might be using ECT1. But so there are uncertainties here around ECT1, for example, and which traffic they assist. And if actually more APIs allows application level to set ECT, you might see more random things happening.
Maybe as an answer to that, I think the stacks can put ECT1 on by default if they support L4S traffic, and they can fall back to the ECN 0 behavior if they detect that there is an ECN queue in there, and if they detect loss, they will also behave similar way as loss. So it's actually not necessarily a decision of the application, because any application can use it. Of course, it depends a bit on
so, I mean, I'm especially worried around if you have actually an open interface to be able to send UDP packets with ECT settings, and it's controlled from application, for example, any Android application or any iOS application, then you're going to see, it's not going to follow your specification. You're not even going to read it, just going to fiddle around with it and try it. And you will have no fallback procedures, anything like that, if it's give them better performance. So it might have some indication that so, but it's, yeah.
All right. We're almost back on track. That's really good. So in the grand tradition of changing the hum questions at the last second and making we're editing things a little bit. So the first, because we observed that the first and the second are basically almost the same thing. So what I would rather ask as the first question is whether, after listening to the presentations today, specifically the earlier presentations on the technology, whether people believe they understand, you know, the proposal that's been brought forward in terms of what it, you know, which pieces it contains of. Okay, I'm making a really long hum question. Do people think they understand the L4S proposal? Yes or no as for any hum. If you believe you understand the L4S proposal, hum now. Okay, if you believe you need more information to understand the L4S proposal, hum now. Okay, I would say that is rough consensus for understanding the technology. So do you believe this is worth the IETF's time? Meaning, do you believe this is something that the IETF should take on? Please hum now. Okay. If you believe that is not something the IETF should take on, please hum now. That is pretty clear. Yeah, at this point, we're going to ask the next two questions, and we're going to do this, I think, with a show of hand, right? Because the proponents will then immediately write down your name. So, who would like to help with the work in the broadest sense? So I see. Yeah, so, okay, I would think that there's probably 20 hands up at the moment. My suggestion would be that, oh yeah. Send an email to the TCP Prague at IDF.org list saying, I'm willing to help, if you are willing to help. And since we have the same problem with the next question, I think state if you would also be willing to help with reviewing of the documents or writing of the documents, and what capacity you would be willing to help. That was the questions we had up here. I don't know, Mirja, if you have anything else you would like the room to hum on for you, since we have a couple of minutes left.
I'm not Mirja, but I wanted to ask there was one whole piece that wasn't discussed here, and I wanted to ask if.
Okay.
The question is specifically about deployment and about who's willing to deploy L4S.
Excellent addition.
So it wasn't asked anywhere, so I really want to raise that question and have a discussion about it, but I don't know that we have time for it now.
No, we don't. But what I would want to do, and this is a good suggestion, if you are in a position where you can, you know, help deployment of this technology, either because you are an implementer of end systems, or if you are a vendor of equipment, or if you are an operator that is buying one of those two, and you are interested in doing so, assuming the technology delivers on the promise, please show your hand. So I'm seeing about, again, 20-ish, maybe 15 hands. Yes. Ericsson and Nokia will be in touch with you shortly. Great. You want to send him in?
I'm trying to figure out how to find something out about the mismatch of people not understanding what L4S is and think it's still worth time in the IETF. So basically, I guess the question is also, do people believe that the IETF is able to do this work?
Okay.
Just to get a sense of the room.
Sure, I'll ask that. If you believe that the IETF is the right place to do this work and we're capable of doing this work, please hum. If you believe that is not the case, hum. Jana has another suggestion for me.
A suggestion, yes, perhaps, because there are many pieces in here. And again, there's the dual queue and the coupling piece, there's the ECN signaling piece, and then there's the response, which is the condition control piece, which I don't think is ready for standardization yet. But we haven't asked that question.
Right.
There were no initial proposals there, no documents to start off of. So I'm not exactly sure what we are asking about in terms of standardizing.
Right. So this is not a working group forming BOF, right? And that's why we didn't, for example, talk at all about whether this should be experimental or standards track or which piece is what, right?
Fair enough.
Also because some pieces are already in flight elsewhere. The structure of how the work gets structured is something that Miria as the ID gets to decide if she decides to charter it. Marcelo.
In my slide, I did have the intended status, and most of it was experimental.
Right, so that was the intended status as intended by the proponents.
I do wonder if the IRTF specifically, I'm actually not wearing my ICCRG chair hat, but I'm asking if the TCP Prague or the sender response really belongs in ICCRG and not in any other standards group.
That's for her to figure out.
Yes.
Yeah, so we will figure that out. The comment I still wanted to make is that the only thing that really, really needs standardization is the identifier. So that's basically one document. Everything else is additional work that explains and helps people to deploy this stuff. So that's one of the reasons why we don't have a working group farming graph, because it's not clear how much work there actually is that needs standardization.
So if you want an input into how the work's organized, talk with Mia. If you want to hear about and see a demo of comparing L4S with FQ Coddle, I don't know if Dave Tat is back. He was particularly interested in that. Excellent. So Kuhn will show that now. The meeting's finishing, but Kuhn will show that now at the front. I guess we can keep displayed. There's a 20-minute break, so I guess you'll see it on the screen for 5 minutes or so, and people who are remote will then be able to continue watching it as well.
Yeah, put it up on the screen, and we are done.
We're done.
Thank you very much.
And thank you to Steve for the notes.
Yeah. That one way better than notes.